When we're working with functions, we often have equations that we call explicit functions where y is written as a function of x. That's called an explicit function. So it tells us exactly what y is. So y equals 1 minus x is an explicit, there's a typo there, explicit function. Okay? So something like this, that's explicit. If you tell me what x is, then I can tell you what y is. All right. However, sometimes we have x and y that are on the same side. So if we have x and y on the same side, then we get what we call an implicit function. Okay, so these are implicit functions. So here's some examples. We have an implicit function like this, y equals x squared plus 3x minus 2, so a polynomial. Or we can have an explicit like this, x sine of all this. We can have a rational function like this. Those are all explicit. Implicit functions are like these. X squared plus y squared equals 25. Or this one which has x's and y's all mixed up and some powers. Or we can have some crazy combination of x and y's. Now, some of these we could solve for y. We could solve this for y and make it explicit. We could solve this for y. But this one, you're not going to be able to solve this for y. And not very easily. It's probably impossible, actually. So we want to be able to take the derivative here of these functions even if we can't solve for y. So we have a method for doing that. That's called implicit differentiation. All right? So the key here is going to be the chain rule, because we're going to remember here that the chain rule gives us a way of differentiating functions, and we want to remember that y is a function of x. All right? So everywhere that we see y down here, think of it as some function of x. All right? So let's look at a couple equations. Well, here we have an equation for y equals x plus 1, a pretty simple function. So if we take the derivative here, the derivative of y, well, the derivative of x plus 1 is just 1. So dy dx is 1. The derivative of 1 just goes away. Here, the derivative of this, dy dx, well, this is x to the negative 1. So let's drop that negative 1 down and write this as x subtract 1. We get negative 2. So this is negative 1 over x squared. And the derivative here, dy dx, is 2x to the first. Now, those are all explicit functions there. Now let's look at the same function in implicit form. Okay, so here we have a function. This is actually the same thing. If you add x, you're going to get this. Okay, and we want to see that we can take the derivative here. We can find the derivative without ever knowing exactly what y is, or without solving for y. So the key is we're going to want to take the derivative of both sides. So we're going to find the derivative of y minus x. And we're going to take the derivative of 1. Now remember, when we say d dx, that is an operator. So we are doing something here. We are finding the derivative of this. Okay? Now, keep in mind here, we've got y, and y is some function of x. Think of it like this. We don't know what this is. Okay? Y is some equation that has an x in it. All right? And but we don't know. It's a mystery. So keep that in mind as we do this. Well, what's the derivative? Let's start on the right side. What's the derivative of 1? Well, the derivative of 1 is 0. And now let's come over here. What's the derivative of y? Well, I don't know what y is. Y is some function. It's a function of x. And so what's the derivative of y? Well, it is the derivative of y. In other words, I don't know, so I'm just going to write down dy dx. Now I need to find the derivative of this minus x. What's the derivative of minus x? We can't find the derivative of that. The derivative of that is 1. Okay. Well, we can solve this. Now remember, our goal is to find dy dx. So we want to get dy dx by itself. So let's get that 1 out of there. And so dy dx equals 1. So notice we never really knew what y was. and we ended up with the same derivative as we got over here. Okay. Now you might say, well, that was a mess. That took more steps. Well, yeah, in this case, we would just solve it the way we did originally. But notice, we were able to find the derivative even though we never knew exactly what the function y was. Okay? All right. Well, how about this one? So we got a product here. So x times y. So we need to find the derivative of the first times the second. We're going to use the product rule here. Well, first, let's do this. Let's write this out. The derivative of xy equals the derivative of 1. Okay? Well, let's start with the right side. The derivative of 1, that's easy. That's 0. The derivative of the left side, well, we're going to need a little bit of product rule because this is x times y. And again, y is a function of x. Okay? So let's take the derivative of the first, we got the first and second. Derivative of the first thing, well, that's derivative of x is 1, times the second thing, y, plus the first times the derivative of the second. Well, the derivative of the second is dy dx, because we don't know what y is. Okay? Well, now our goal here is to solve for dy dx. So let's rewrite this once here. We got y plus x times dy dx equals 0. Got to get that y out of there. So let's get that y. And so we have x dy dx equals negative y. Okay? Now, let's solve this up. All right, so we got dy dx times x. So let's divide both sides by x. And we are done. So we have dy dx. Let's go over here. dy dx equals negative y over x. Okay? So we found the derivative in terms of y and x. So we can now find the derivative at any point. If we know the x and y value, we can just plug them in, and we can find the derivative. Okay? All right? Well, how about this one? Now, again, we could solve this for y. Okay, now notice this is, if we take this equation and we divide it by x squared, we get this. Okay, so yes, we could solve this for y, but that's not what we want to investigate right now. Right now, we want to take the derivative of both sides. Okay, we want to see how we can do this implicitly. Okay. The derivative of 1 is 0, and we've got a quotient here. So let's do our quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom. Okay, so let's do that. Derivative of the top is dy dx times the bottom minus the top times the derivative of the bottom, which is 2x. Okay, and now we want to solve this for dy dx. Okay, so we got to get this out of there. Let's maybe clean it up one time. Dy dx times x squared minus 2xy equals 0. Okay, what do you want to move first? Well, let's get that 2xy out of there. So let's add 2xy. All right. And we have x squared dy dx equals 2xy. And last but not least, let's divide by this x squared here, or multiply by 1 over x squared. And we end up with dy dx equals 2xy all over x squared. A little bit of simplifying here. X goes into there once. Okay, we can cancel that out. And so last but not least, dy dx is 2y over x. So this turns out to be a real useful tool because we don't need to find out what y is. So the key steps here are we want to take the derivative of both sides, evaluate the derivatives, and solve for dy dx. Okay, let's see how that works here. So here we have a function, x squared plus y squared equals 25. Okay, now by the way, this is actually not a function. If you graph this, it's a circle. So this is a circle with a radius of 25, actually a radius of 5. Okay, centered at 0. and that is not a function. So we can now take the derivative of things that aren't necessarily functions. Okay, so what we're going to do is we're going to take the derivative of this side and the derivative of this side. Okay, the derivative of 25 is 0. And let's take the derivative of each of these parts separate. What's the derivative of x squared? Well, that's 2x. And what's the derivative of y squared? Now, I've got to be careful. Again, remember, think of y as some function of x. All right, we're not going to solve for y. We could kind of here, but we're not going to. So, but that requires the chain rule. So we got to take the derivative of the outside. The derivative of the outside is just 2y. But you also need to take the derivative of the inside. The derivative of the inside is dy dx. Because we don't know what the inside is exactly. Some mystery function like this, okay? So that's the key there, all right? So now the question is, what is the derivative? Well, we can solve this. Subtract 2x from both sides. 2y dy dx equals negative 2x. Okay, and now we can divide both sides by 2y, and we get dy dx is negative 2x over 2y. And cleaning that up, we have dy dx is, cancel out the 2's, negative x over y. Pretty simple equation there. Okay, so there's our derivative in terms of x and y. Well, let's see how we can use that. All right, so here's a question now. We want to use implicit differentiation to find dy dx. We kind of did that for this one already. And then we want to find the equation of the tangent line at this point. Okay, and you can use Desmos to graph this and check it out. So we just found the derivative, so we won't go through that again there. Okay, so we know that dy dx is negative x over y. Okay, so now if we evaluate this at 3, 4, so we can write it this way, the derivative, whoops, dy dx, sorry, dy dx. Now here's a little notation that's good to get useful. We're going to evaluate it at 3, 4. This vertical line means evaluate it at. Okay, so we're going to evaluate this at 3, 4, right? 3, 4. So the derivative is negative 3 over 4. Okay, so that's the slope there, all right? Well, if that's the slope and we know it goes through 3, 4, then we can write an equation of our tangent line. The tangent line is y minus y1, which is 4, equals the slope, negative 3/4, times x minus x1, which is 3. Okay, if we solve this up here, let's go and put in slope-intercept form so we can see it easily. If we distribute negative 3/4, we get negative 3/4 x, and this is going to be 9/4. Add 4 to both sides, and this is going to be y equals negative 3/4 x. And if we add 4, which is 16/4, that'll be 25/4 plus 25/4. So let's graph this point. We find the point 3, 4 here. So 3, 4 right there. We've got a slope of negative 3/4, going down 3, right 4. Up 3, left 4. Okay. And this should be our tangent line here. So if we go like this, there we go. Pretty close. See if I can get that to move. There we go. All right, so there it is. Okay. And that's our equation, that's our line. That's how it works, okay? Let's look at a couple more and we'll call it good, all right? So if we want to draw the tangent line of this graph here, okay, well, again, we've got a function that is an interesting function if you graph it there. So let's find the derivative here, d dx. Take the derivative of both sides. Okay, take the derivative of the whole thing. So we'll just go like this. Take the derivative of the whole thing, both sides. Derivative of the right side is 0. Derivative of the left side, well, we have to do the chain rule here. So we take the derivative of it as it is, 2y. But remember, y is a function of x. So we need to multiply that by dy dx. Minus, take the derivative of x cubed, and we get 3x squared. Take the derivative of 2x, 2. Now we need to solve it for dy dx. So let's get all this stuff that doesn't have a dy dx onto the other side. So let's subtract the 2. Let's add a 3x squared. And we end up with 2y dy dx equals 3x squared minus 2. And now let's divide both sides by 2y. So dy dx is 3x squared minus 2 all over 2y. All right, there you have it. Found the derivative. Now we can find the derivative at 0y, so at 0, 1, sorry. So the derivative dy dx evaluated at 0, 1 is going to be 3 times 0 squared minus 2 all over 2 times 1. Okay, negative 2 over 2, which is negative 1. So the slope is negative 1. And so our equation, y minus 1 equals negative 1 times x minus 0. Little cleanup. Y minus 1 equals negative 1 times x, which is negative x. Add 1 to both sides, negative x plus 1. Okay? There you have it. Here's that curve there. Kind of an interesting curve. So here's that graph. This is actually something called an elliptic curve. Kind of interesting. Probably never seen anything like this before. And so you're not going to solve this for y. Not going to be able to do that. Well, you could solve it and get, I guess, a piecewise function. But anyways, here's a graph. And we found this tangent line y equals negative x plus 1. There it is. Now, by the way, it does cross the graph over here. But when we say tangent, that means in the neighborhood, or for all points near this, it only touches the graph once. Okay? So that's how that works. All right. So how about this one here? All right. So let's take this function and let's find the derivative. Now, directions say find it at a point that you find. Find the coordinates of a point on the graph first, okay? So, well, we need to find a point on the graph maybe. What happens when x is 0? So we try an easy one. When x is 0, 0 times sine y plus y times cosine 0 equals 4 pi. Well, let's see. This is 0. So y cosine of 0 is 1. And so that means y is 4 pi. Okay, so we found a point. The point is 0, 4 pi. That's on the graph. All right. So let's take our derivative here. So let's take the derivative of the whole thing. The derivative of this here, all right. Derivative of the right side is 0. Now the derivative of the left side here, all right, we're going to have some product rule. We got two parts. So here we go. Let's go derivative of the first. Derivative of x is 0. I'm sorry, it's 1. Derivative of x is 1. Derivative of the first times the second plus the first, which is x, times the derivative of the second. Well, the derivative of sine y is going to be the derivative of sine, which is cosine y, times the derivative of the inside, which is dy dx. Plus, let me move this 0 out of here for a second. Plus, now that was just the first part here. Let's go to the second part here. Okay, so I need the derivative of the first, which is dy dx, derivative of the first part times the second, cosine x, plus the first times the derivative of the second. Derivative of cosine is negative sine x equals 4 pi. Actually, sorry, equals 0, because the derivative of the right side is 0. All right, so there's an interesting mess. Okay, so we need to solve this. In order to solve this, we want to get all the stuff that doesn't have a dy dx over on the other side. So let's take this part, because it doesn't have a dy dx, and this term. Let's take those to the other side, all right? So we have, let's subtract sine y from both sides. That's going to get it over to the right. And this is a negative y sine x. So let's add that to both sides. Y sine x. It's a negative because that negative's in there. And on this side, we have x cosine y times dy dx plus cosine x dy dx. Now notice they both have a dy dx. So that means we can factor that out of this x cosine y plus cosine x equals negative sine y plus y sine x. Okay, so we factored out the dy dx, and now, last but not least, we can divide by this whole thing in the parentheses, x cosine y plus cosine x. X cosine y plus cosine x. And that leaves us with dy dx equals this fraction we have here. Negative sine y plus y sine x all over x cosine y plus cosine x. Okay, there you have it. All right. Well, last little part here. What if we take second derivatives? Well, this gets a little interesting here, all right? So we want to find the second derivative. This is the second derivative. Okay, d2, that d2 means the second derivative. And we want to find it as a function of x and y. All right? To do that, let's take the derivative of both sides. So we're going to take the derivative of 2x cubed minus 3y squared equals the derivative of 8. All right side is going to be 0. So the derivative of the left side, we have 6x squared minus, take the derivative now of this whole, the outside part. In other words, kind of just treat it like an x. So this would be 6y to the first. Now take the derivative of the inside, which is dy dx. Okay. Solving this up, let's get the x's on the other side. Negative 6y times dy dx. Subtract that 6x squared over, moving this over there. And now we need to divide by negative 6y. And that gives us dy dx equals the 6's cancel, x squared over y. All right. Well, there's the first derivative. That's part way there. Now to find the second derivative, we need to take the derivative of the derivative. So we're going to take dy dx on the left, and we're going to take the derivative of that. We're going to take the right side, x squared over y, and we're going to take the derivative of that. Well, the derivative of the derivative on the left is the second derivative, which we write as d squared y over dx squared, okay? Means the second derivative. We have a quotient on the right, so we're going to need to do a derivative of the top times the bottom minus the top times the derivative of the bottom. Okay, all over the bottom squared. So the derivative of the top is 2x times the bottom minus the top times the derivative of the bottom. What's the derivative of the bottom? It is dy dx. All over the bottom squared. Okay. All right, now we're almost there, But notice the instructions. We want to find the second derivative as a function of x and y. Is this a function of just x and y's? Nope. We've got a dy dx in there. So we've got d2y over d. Last thing we got to do is we've got to substitute. Well, what is dy dx? Well, it's right here. We know what it is. Dy dx, we found it along the way. So we can substitute for that. Let's do that right now. So we've got 2xy minus x squared times x squared over y. So we're going to substitute there for dy dx all over y squared. Okay. And this is 2xy minus x to the fourth over y all over y squared. We'd like to clean this up a little bit. We don't like this compound fraction. So if we multiply the top and the bottom by y, that common denominator there, that only denominator I should say. Okay, we want to cancel this out. So distribute that thing and we are done. So we'll distribute that 2xy squared minus x to the fourth all over y cubed. There is the second derivative. Okay? All right. And that's going to be useful for finding the acceleration soon. All right. So, second derivative, a little bit of work, but that's the idea. Once we find the first derivative, take the derivative again, and there will be a little substitute to get it back to x and y's. All right, great. Well, that is implicit differentiation. All right, it's a little different there. Remember, when you're taking the derivative of something with a y, we need to use the chain rule. That's the key. So, great job. Thanks a lot.